Hi everyone, welcome back. We're going to be working on a 9.6 probability. We're going to do an example of each type of probability problem. And the essential question is, how do I find the probability of events? Okay, so there will be quite a bit of copying to do. We are going to copy down several formulas. Most of them are actually pretty simple to use. Okay, so the first one we're going to look at is this one that says the probability of an event. So here it reads, if an event E has n parentheses E equally likely outcomes, and its sample space S has n parentheses S equally likely outcomes, and then the probability of event E is given by all of that. Now, all of that actually makes it a little more confusing than it really should be, but essentially what we're looking at is this. P of E is the probability of an event. N of E is the number of times the event can occur. And then NS is talking about all of the possible events in that sample. So with this idea, we're talking about what can happen versus what we want to happen. All right? So with the first example, we'll keep it pretty simple. Example 1, probability of getting heads twice from a coin toss. So in this event, what we're talking about is throwing up two coins, or actually throwing up a coin once and then throwing it up again. So if we were to list out the possible outcomes, what I would have is heads, heads, which is the ideal, or the event that we want. The other event could possibly be getting heads once, then tails the second time. The other one could be tails 2 times, or we could get tails first and then heads the second time. In this case, the event that we want only happens once. The total number of events in this sample is 4. So the probability of the event that we want, getting heads twice, is going to be 1/4. All right, so it's really actually just that simple. We're talking about what we want versus everything that could happen. Okay, so that's basic probability. The other type of probability, what we're going to focus on, uses this idea in addition to adding in some like barriers that we kind of impose. So here we're going to be talking about mutually exclusive events. When I'm talking about mutually exclusive, we're saying that the event of one thing doesn't overlap at all with another event. Okay, so it will make more sense with the upcoming example, but go ahead and copy down this box, probability of the union of two events. So if A and B are events in the same sample space, then the probability of A or B occurring is given by this. So P, the probability of A with the union B is equal to the probability of A plus the probability of B minus the probability of A and B happening at the same time. Over here, this is just kind of additional pieces because it's the same exact formula, but it doesn't include this part. The reason is because if we're saying something is mutually exclusive, it means that there is no overlap, so I don't have to subtract anything anyway. All right, so we're going to go ahead and do the next example now. With example 2, we're going to consider a deck of cards. So remember, a deck of cards has 52 cards, 4 different suits, and in each suit we have 13 kinds of cards. So the event that I want is the probability of getting a spades, so of drawing a spades or a face card. A face card, we mean a jack, queen, or king. All right, so with this one, you can draw a Venn diagram to help you organize your thoughts. Here we would have spades and everything that goes in there. Here we would have the face cards. And then obviously in this overlap, we have faces of spades. Considering that we only have 3 faces we're talking about the jack of spades, the queen of spades, and the king of spades. Every other spade card, so 2, 3, 4, 5, 6, so on and so forth, will fit into that category. For face, this one's going to be a little more confusing because I'm not going to do all the notation, but it includes the hearts, diamonds, and the clubs. Okay? So all of those guys fit in here. And now we're going to consider the probability of each event. So first off, I want the probability of drawing a spades. The other one is the probability of getting a face, because I'm fine with drawing either one of those cards. However, I also have to subtract the probability of getting a face of spades, because that's going to be our overlap. And we don't want to double count any specific card or number, because then we're technically raising the probability, and that would be lying to ourselves. So here, the probability of getting a spades, as we said, there are 13 cards within each suit, so 13 out of 52, the entire deck. Probability of getting a face card, there's 3 faces in each suit, and there's 4 suits, so I know there are 12 out of 52 there. But then I have to subtract that extra counting of 3 over 52 because I don't want to double count the faces of spades. All right, they're already counted in one of them. We don't want to count them again, so we have to take away that double. Now, we're going to simplify. That's going to be 25 minus 3, 22 over 52. Simplified, our probability is 11 over 26. Not such a bad probability if we were trying to get a specific card like this, okay? The final idea of probability are independent events. So here, we're talking about independent events in the idea that 2 events don't affect each other whatsoever. So if I do one thing, the other event has no control over it, has no influence over it. So if you're thinking about rolling a dice or a die, the next die you roll shouldn't have any impact on the previous dice, or the other dice shouldn't have, so on and so forth, based on that idea. Go ahead and copy this box, probability of independent events. So if A and B are independent events, then the probability that both A and B will occur is given by, so probability of A and B equals probability of A times the probability of B. Now these events could be actually the same. So let's say that the example is we want to roll a 6 on both die. We would get 1 over 6 for the first probability times 1 over 6 again. All right, so for our example, we're going to go ahead and go with the dice, but we're going to make it a little more interesting. Example 3. We have the question is the probability of getting 3 or lower on each dice roll. And to be specific, we're talking about one after another. Because some people might think that rolling 2 dice together at the same time somehow influences it. So, the event A that we're talking about is the idea of getting a 3 or lower. So there's 1, 2, and 3 out of all the numbers in a dice, which are 6. So the probability of this event is 3 out of 6, which is 1/2. So the probability of this happening 2 times in a row, so in other words, getting both of them, is the probability of A times the probability of A. And that's going to be 1/2 times 1/2, which means we have a 1 in 4 chance of rolling this dice 2 times and getting 3 or less every single time. All right, so that's pretty much the idea of probability, one example for each one. We're going to see a ton more examples tomorrow, so make sure that you understand what's going on at this level. Write in any questions that you have and go ahead and move on to the Google Forms. See you guys tomorrow.